Hi everyone and welcome to the Learning Curve Academy. In this video, I will be looking at one of the most popular areas in the study of Calculus 1, namely to find the critical points of a function and classify them as local, relative maximum, relative minimum, or saddle point. And we will be using the principle of partial differentiation to solve this problem. So here we are asked to find the critical points of this given function and to classify them as relative max, relative min, or as a saddle point. And in order to find the critical points of the function, we need to find fx and fy. That is, we need to differentiate the function with respect to x and with respect to y respectively. So that's the first thing we need to do in order to find the critical points. So to find the critical points here, we're going to find fx, which means that we're going to differentiate with respect to x, the given function. So differentiating this given function with respect to x, when we differentiate negative 2x squared, we will get negative 4x because the power of 2 comes down and multiplies by the negative 2 at the front, and we take 1 from the power. So we get negative 4x raised to the invisible power of 1. Then when we differentiate negative 2xy with respect to x, then it means that we're treating y as a constant. So y would be treated as a constant in the same way that negative 2 is a constant. So the constant coefficient of x here would just be negative 2y. So that's the derivative of negative 2xy. When we differentiate negative 2y squared, the answer would be 0 because all of this would be a constant, and when we differentiate a constant we get 0. Because we're differentiating with respect to x, y is treated as a constant. So this entire expression would be treated as a constant when we're differentiating with respect to x. Then this would be plus 36 because when we differentiate 36x with respect to x, we just get the coefficient of x, which is 36. And again, with respect to 42y would be treated as a constant because we're differentiating with respect to x. So that will be plus 0. And of course, when you differentiate negative 158, we get 0 as well. So when we simplify this, this becomes negative 4x. Take away 2y plus 36. And that is our solution for fx. Now let's find fy, which means that we're going to differentiate this function, the given function, with respect to y, treating x as a constant. So differentiating with respect to y, negative 2x squared would be treated as a constant. So when we differentiate constants, we get 0. When we differentiate negative 2xy, then negative 2x would be treated as the constant coefficient of y, since we're differentiating with respect to x. So the answer there would just be negative 2x. Good. Now when we differentiate negative 2y squared with respect to y, we get negative 4y. And when we differentiate 36x with respect to y, we would get 0 because the entire negative 36x will be treated as a constant. And when we differentiate 42y with respect to y, we'll get 42. And of course, when we differentiate negative 158 with respect to y, because negative 158 is a constant, that would be 0. So now when we simplify this further, this will be negative 2x, take away 4y plus 42. And that is the value for fx and fy respectively. Now the next thing we need to do to find the critical points is that we need to set fx equal to 0 and we're going to solve. We're going to set fx equal to 0 and we're also going to set fy equal to 0, and then we're going to solve for x and y. Okay, so here we go. We're setting fx equal to 0 and fy equal to 0. And when we solve for x and y from these, that would enable us to find our stationary points or critical points. So fx equal to 0 here would be negative 4x minus 2y plus 36 equals 0. And negative 2x minus 4y plus 42 also equal to 0. And what we need to do here is to solve for x and y. So we're going to do a little bit of transposition. So we're going to have in equation number 1 here, let's call that equation number 1, and let's call this equation number 2. In equation number 1, I'm going to keep 36 on the left-hand side of the equation and bring 4x, negative 4x, and negative 2y to the other side of the equation, so they would become positive on the other side of the equation by inverse operations. Similarly, for the equation number 2, I'm going to keep 42 on the left side of the equation, and negative 2x, when it goes on the right side of the equation, on the other side of the equation, it will become positive. So too, negative 4y would become positive. So this is the rewritten form of the equations 1 and 2. And so since we have two separate equations here with two unknowns, we can easily solve these equations simultaneously. So I'm going to just rewrite the two equations here, and I'm going to solve them simultaneously. So 4x plus 2y is equal to 36. And of course, 2x plus 4y is equal to 42. Two equations, two unknowns, so we solve these simultaneously. Applying the principle of simultaneous equation here, I'm going to multiply the second equation here by 2 in order to get the coefficients of x to be the same, and then that will allow me to eliminate x. So I will have 4x plus 2y equals 36, so equation 1 will remain the same. 4x plus 2y equals 36, and equation 2 would become 2 multiplied by 2x, which is 4x, and 2 multiplied by 4y there, which would be 8y, and 2 multiplied by 42, which is 84. The whole point of multiplying by 2 is to get the coefficients of x to be the same in order to allow us to solve simultaneously by eliminating the x. So now we're going to subtract the two equations. Equation 2 subtracted from equation 1. So 4x minus 4x is going to be 0, so that will be gone. And then I have 2y minus positive 8y, which is going to be negative 6y. So it's going to be negative 6y. And then, of course, we have 36. Take away 84, right? We have to subtract on that side of the equation as well. It's the entire equation 1 minus equation 2. So 36 minus 84 is going to give us a negative 48. And so we can easily find y here by dividing both sides of the equation by the coefficient of y, which is negative 6. So when we divide negative 48 by negative 6, we will get an answer of 8. So here we have found the value of y to be 8. Now, since we have found the value of y to be 8, we can therefore substitute this 8, which is the value of y, into any of the two equations here. All right, we're going to substitute it into any of the two equations, either this equation 4x plus 2y equals 36 or 2x plus 4y equals 42. So by elimination, we eliminated x and we found that y is equal to 8. So therefore, 4x, we're going to substitute it into this equation, the first one. 4x plus 2 multiplied by y, which is 8, will give us 36. All we have done here is to substitute 8 for y in this first equation. So we will have now 4x plus 2, 8, 16 equal 36. So this would leave us with 4x equal 36 take away 16. By inverse operation, the 16 would become negative on the other side of the equation. So then 4x is equal to 36 minus 16, which is 20. So that 4x would be equal to 20, so x is equal to 5, which is that number that is multiplied by 4 to give 20. That's obviously 5. So now we have found the critical points. The critical points are x being 5 and y being 8. So I write them in coordinate form. So those are the critical points of the function. x5, y8. So by taking the first derivatives, partial derivative with respect to x and partial derivative with respect to y, we were able to apply the necessary mathematical techniques to find the stationary points or the critical points of the function. The other thing that we have to do now is to make a determination as to whether these points are a relative maximum, whether this coordinate here, 5, 8, represents a relative maximum or a relative minimum or a saddle point. And to do that, we need to take some second derivatives. So we're going to find fxx, which means that we're taking a second derivative with respect to x, partial derivative with respect to x. I'm also going to find fyy, yes, and we will also find fxy, but fxy would also be the same as fyx. So once we find fxy or fyx, we know they will be the same. Now to find fxx, it means that we're going to differentiate fx, which is this here. This is fx. So it means that we're going to differentiate fx with respect to x. That's what fxx means. When we differentiate fx with respect to x, differentiating negative 4x would give me negative 4. Because we're differentiating with respect to x. When we differentiate negative 2y with respect to x, y is treated as a constant, so that would be 0. And of course, when we differentiate 36, we'll get 0. Now for fyy, we're going to differentiate the fy with respect to y. So let's look at this. So we're differentiating this expression, this function here. When we differentiate negative 2x with respect to y, we would get 0. But when we differentiate negative 4y with respect to y, we'll get negative 4. So that's fxx and fyy, and of course 42 is a constant. So when you differentiate it, you'd get 0. Now for fxy, fxy now means that we're going to take the partial derivative of x with respect to y. So that means we're going to differentiate the fx function here in terms of y. So when we differentiate this fx function with respect to y, then negative 4x would be treated as a constant, so that goes to 0 when we differentiate with respect to y. But when we differentiate negative 2y with respect to y, we get negative 2. And when we differentiate 36 with respect to y, we will get 0 as well, because that's a constant. fxy is the same as fyx. Okay? So now I have fxx, fyy, fxy, and fyx. And we simply just write this in matrix form. I'm going to now write this answer in matrix form. So to write this answer in matrix form, this is what we're going to get. We're going to get, writing this in matrix form, we put fxx here first. fxx is negative 4. And fyy, we put them on the leading diagonal. fxx and fyy, we place them on the leading diagonal. And we place fyx and fxy on the remaining diagonal, on the off diagonal. So that is the matrix that we form from the results, which we're going to call that matrix H. So calling that matrix H, H is equal to this. And so all I'm going to do now is to find the determinant of H. So finding the determinant of H here, we will get negative 4 multiplied by negative 4, which is positive 16, and negative 2 multiplied by negative 2 is 4. 16 minus 4 is going to give us 12. So we have reached the ultimate stage now where we can determine here that since h determinant is greater than 0 and fxx is also less than 0, remember we found fxx to be negative 4, so ffx is less than 0, and the determinant of the matrix here is 12, which is greater than 0, then we conclude that we have a relative maximum at the coordinate 5, 8, which is the critical point or turning point for this function. So at the critical or turning point 5, 8, we have determined that there's a relative maximum. And the reason why we were able to find that there's a relative maximum, or to deduce that there's a relative maximum, is because when we took the determinant of the matrix here, the matrix of the partial derivatives, we got 12, which is greater than 0. And therefore, from there, we just need to evaluate fxx to determine if it is less than 0 or more than 0. Since it's less than 0, negative 4 is less than 0, we conclude that there's a relative maximum. If it was greater than 0, if fxx was greater than 0, having concluded that the determinant is greater than 0, if fxx was found to be greater than 0, then we would conclude that there's a relative minimum. But in this case, because it's less than 0, we conclude definitively that we have a relative maximum at the critical point 5, 8, which we found earlier. And that, ladies and gentlemen, is how we find the critical point of an implicit function like this using partial differentiation. Thank you very much. I hope you found this to be clear and easy to follow, and I hope you will continue to tune into this channel for much more. Remember to like, share, and subscribe. See you soon on the learning curve.